Hey folks, I'm going to do a couple of examples with you guys today here. We're going to take a look at how to do some titration calculations questions. That's the point of what we're working on today. And I have an example here where 23 mils of 0.7 molar hydrochloric acid is neutralized with 15 mils of calcium hydroxide. And we don't know the concentration, so that's what we're going to try and figure out. I can see that I know my volume and my molarity for my HCl. And I know my volume of the base, but I don't know what its concentration is. So anytime we have to do any kind of a question like this, our first step always has to be to do a balanced equation. And so here I'm writing the balanced equation, hydrochloric acid plus calcium hydroxide. And when I go to do this kind of a reaction or any other kind of double displacement reaction, the first thing I do is I think about what ions are available. So from the hydrogen chloride, the hydrochloric acid, we can see that we're going to get hydrogen plus 1 ions and chloride minus 1 ions. From the base, from the calcium hydroxide, we see that we get calcium plus 2 ions and hydroxide minus 1 ion. So what are the other positive-negative combinations that I can make? Well, the hydrogen can join with the hydroxide, and this will make water, H2O. Lots of times we'll write water as HOH, hydrogen hydroxide, because it makes it easier for us to balance the hydrogen separate from the hydroxides. We can also combine the calcium with the chloride. Use your symbols, charges, crisscross reduce to get the formula. Calcium chloride is CaCl2. Now this is not balanced, so our next step is going to have to be to balance this reaction. We've got to balance this equation in order for things to work. I see that I've got 1 hydrogen and 1 chlorine from the hydrogen chloride, but on the other side of the equation there's 2 chlorines. So putting a 2 in front of the HCl takes care of the chlorines. But now we have twice as many hydrogens, so I have to put a 2 in front of the water. Notice that water is HOH, so it's just the hydrogens from the acid that I'm balancing. I need 2 of those hydrogens. I can see that this 2 also means that I have 2 of the hydroxides. Those came from the base, and there's already a 2 there. There's already 2 hydroxides in front of the base, so that's already balanced. And I see 1 calcium before and 1 after. So we can put in the numbers 2, 1, 2, 1 for our balancing. Normally we wouldn't write the number 1s in chemistry, but I want us to be aware that there are balancing numbers there as well. Our next step, whenever we have a titration calculation question, is to write our formula, VACA equals VBCB. So we're going to have the volume of the acid times its concentration is equal to the volume of the base times its concentration. But we have to look at our balancing. In our balanced equation, in front of the acid, the HCl, there's a 2. That means we're going to put this 2 in front of the base side of our math equation. It trades places. Calcium hydroxide is our base. There's a 1 in front of our base, so in front of the math equation, we put a 1 in front of the acid side. So they go with the opposite. Pay attention to which is the acid and the base. We can now substitute into the equation with the numbers from the problem. We can see the volume of the acid was 23 mils. The concentration of the acid was given to us as 0.7 molar. Keeping the 2 on the other side, the volume of the base used was only 15 mils, making sure that we have the same units on both the left and right side of the arrow, of the equal sign, and the concentration of the bases are unknown. So now I want to solve for CB. I can see that right now concentration of base is being multiplied by both 2 and 15. So to get CB by itself, I'm going to have to divide that side of the equation by both 2 and 15. And what I do to the left, I do to the right. So then I have to divide the other side by both 2 and 15, so that keeps things equal. We can now see that the 2's cancel. The 15 mils both cancel. And on the left side of the equation, just the symbol milliliters will cancel. Bringing up a calculator here. Remembering that we multiply numbers on the top of the line and divide numbers on the bottom of the line. We'll go 23 times 0.7. And we'll divide that by both 2 and 15. So 2 times 15 is 30. And we get a total value of 0.5366, about 0.54. 0.54 what? Well, this is our concentration of our base, and you'll see that the only units we haven't canceled so far are the M for molarity, and that is the correct units for concentration of the base. Okay, here's another possible question. A solution is made by dissolving 28.5 grams of potassium hydroxide in 0.5 liters of water. There's a lot of numbers here, so if you know me, I like to highlight or circle the words in my equation to help them make out what they are. I've got 28.5 grams dissolved in half a liter of water, and I'm going to use 2.5 liters of this solution. Potassium hydroxide is a base. It's being neutralized by 0.136 liters of sulfuric acid, H2SO4. So what's going to be the molarity of my acid? Our first step is always to write and balance the reaction. And we're having a reaction here between potassium hydroxide, KOH, and sulfuric acid, H2SO4. Again, this is a double displacement reaction, so think to yourself, which ions are available? From the potassium hydroxide, we get potassium plus 1 ions and hydroxide minus 1 ions. From the acid, we get H plus 1 ions and sulfate, which are minus 2 ions. What are the other possible positive-negative combinations I can make? Well, potassium can join with sulfate. That will give us K2SO4. Remember to crisscross your charges. And hydrogen can combine with hydroxide. And this time I'm going to write it as HOH because we can see how much easier it makes our balancing. Okay, now we have to balance this equation. Get rid of these numbers here on the bottom because they're going to be in the way for me to work. When I take a look at this equation, the first thing I notice, I've got 1 potassium before the arrow and 2 after. So putting a 2 takes care of that. That also, though, gives us 2 hydroxides, and there's only 1 on the product side. So we'll put a 2 to mean 2 hydroxides. This 2 affects the hydrogens from the acid. There was 2 of them. And we see in our H2SO4 there's already 2 hydrogens. And I see that there's 1 sulfate before and 1 sulfate after. So I can just put 1s in front of both of these parts of the equation. We're now balanced as 2, 1, 1, 2. Because this is a neutralization equation, I'm going to write VACA equals VBCB to do the math. But I know that I have to find the coefficients and put them on the proper side. So when I look at my balanced equation, I see that H2SO4 is my acid, and in front of it's a number 1. That means I'm going to have to put a 1 in front of the base side of my math expression. In my balanced equation, the potassium hydroxide was my base. It has a 2. That means I'll put the 2 with the opposite, the acid side of my math equation. Now I just need numbers to substitute. I know the volume of acid, 0.136 liters. And I know the amount of the base that I use. I use 0.25 liters of the solution, but I don't have a concentration for it. I've been given grams and I've been given liters when I made it, and I'm going to have to figure out the concentration. So in order to do this, I'm going to have to do some stoichiometry. So a quick labeling here, VA is my volume of my acid that I use for the equation. VB will be the 0.25 liters. That'll be the volume of the base in the equation. And we're going to use our other 2 numbers to do some stoich to figure out the concentration of the base. We start by putting our measure over our volume. We've got 28.5 grams over a total of 0.5 liters. But this isn't concentration. Concentration is not measured in grams over liters, it's measured in moles per liter. So I want to get this into the form of moles over liters. So we have to use our molar mass. I want to get rid of grams on top, so I'm going to have to write grams on the bottom. And I want moles, so I'll write moles on the top. And we always put the number 1 beside the word mole. And to figure out how many grams, I have to add 1 potassium, which weighs about 39, with 1 oxygen, which weighs about 16, and 1 hydrogen that weighs about 1. Now I know I'm rounding off, but just to keep things simple, I'm just going to round off to whole numbers, and we get about 56 grams per mole for a molar mass for potassium hydroxide. Okay, let's check to see what units cancel. I see grams on the top cancels grams on the bottom, and I'm left with moles on the top, which is what I want. I'm left with liters on the bottom, which is what I want. So now all we have to do is math. So we'll bring back our calculator, and we're just going to slide this out of the way so that I can show you guys where the numbers are coming from. Clear this out here. Okay, so multiply across the top, divide across the bottom. So 28.5 is on the top. We don't have to times by 1, so we'll just go divide by 0.5 because it's on the bottom, and also divide by 56 because it's on the bottom. And that gives us 1.018 or 0.178, so about 1.01, 1.02. Let's round that up to 1.02. Now this is going to be the concentration of our base. This is my CB. So now I know CB, VB, and VA. We're just going to substitute. The concentration of the base was 1.02 molar, moles per liter, and molar means the same thing. The volume of the base that we used, from up in the question, we said we used 0.25 liters. We don't have to say times 1 because that changes nothing. On the other side of the arrow, the volume of the acid given was 0.136 liters. We've got to keep the 2 there because that definitely would change our math. So 2 times 0.136 liters, and the concentration of the acid is what we're trying to solve for. So again, I want to get Ca by itself. That's the whole point when we rearrange a formula. I'll just scroll up here. So that means that, we're going to have to divide this side by both 2 and by 0.136 liters. And then to keep things equal, I'm going to have to divide the other side by both 2 and 0.136 liters. Okay, we can see now that the 2's will cancel directly on the left, so will the 0.136 liters. And on the right, the only thing that cancels is the symbol liters. The L's will cancel. Okay, let's get our calculators out. Move this over to the other side again so you can see my numbers. Remembering multiplying on anything on the top of the line, dividing anything along the bottom of the line. So here we go. Let's type this in. We're going to go 0.25 times 1.02 because they're both on the top, and then divide by 2 and divide by 0.136. I could have multiplied those two numbers at the bottom together, but I would have had to put them in brackets first. Or I can just divide by everything on the bottom. I get the value of 0.9375, about 0.94. 0.94 what? Well, the only units that we haven't canceled out so far are the units molar, which are the correct units for calculating molarity.